Hey there, physical science students. This is Miss Ruark. This is chapter 14, dealing with heat and temperature, and we're still in our energy unit, so that's why it's still Vodcast 3.4. All right, so temperature. Well, what is temperature? Well, typically when we talk about temperature, we're talking about how hot or cold something is. However, that's not the true definition of temperature. The true definition of temperature is a measure of the average kinetic energy of the particles in a substance. Right, so if the kinetic energy or energy of motion is high, there's a lot of movement, which will be related back to us in terms of heat. So it will be hot. And if the kinetic energy is low, which means there's not a lot of movement, then the temperature will come back as low. All right, there are a couple different scales that we use to measure temperature. The first one that we use, which is not listed here, is the one that you're most familiar with, and that would be Fahrenheit. Fahrenheit is an English measurement system, or is on the English measurement system, and it's used mostly in the United States. In science, however, and throughout the world, we use Celsius and we use Kelvin. Okay, both Celsius and Kelvin are a degree scale, and that's how you can have positive and negative numbers. And you also have the degree sign with the letter C after it, or the degree sign with the letter F after it for Fahrenheit. However, Kelvin is a science scale, and it's actually based, it's an absolute scale. It's not a degree scale. And so it's based on the fact that absolute zero is the lowest temperature you could possibly get, because that's when there is no kinetic energy left in an object. It is completely still. However, absolute zero is kind of a fictitious thing because nobody's been able to reach it. In lab settings, they've come extremely close to it, but they've never been able to reach it before. All right, so when you do your abbreviation for Kelvin, it's just an uppercase K. There is no degree sign in front of it because it's not a degree scale, it's an absolute scale. All right, to change back and forth from Celsius to Fahrenheit, we're not going to have you do that because there's really no need for it. However, you do need to know the Kelvin Celsius degree change. So to change from Celsius to Kelvin, you would add 273 to whatever the Celsius is to get Kelvin. If you want to go from Kelvin to Celsius, Celsius would be equal to whatever the Kelvin is minus the 273. Make sure you have that written down and you know that, because if you don't, well, you're not going to get a lot of help from me when it comes time for our test or quizzes, because that's something that you need to know. All right, heat. What is heat? Well, heat is a form of energy. It's called thermal energy because it's hot. All right, so heat is the energy transferred from one object to another because there's a temperature difference in those objects. Okay? And then once the energy or heat is transferred, the other object doesn't have any more heat, but does not have more heat, but it has more internal energy. All right, so one object touches another object. Let's say when you wake up in the morning and you go to get into the shower, or when you get out of the shower and you step onto the tile floor, it's cold. Okay, well, why is that? You feel that heat difference, okay, because your foot is hotter than the tile is, and so there is an energy transfer going on from your foot to the tile. If you were to heat up, if you're boiling water and you go and touch the pot on accident, your hand is cooler than the pot is hot, it burns your hand, and that's because the energy is being transferred from the hotter object to the cooler object, which would happen to be your hand. Okay, once the heat is transferred and both objects are at, after you're standing on the tile for a little while, your feet don't feel cold anymore. The tile doesn't feel cold, it feels normal, and that's because the heat transfer has happened. There's no more heat to transfer because it's equal, but your foot now has more internal energy because it has soaked up that extra energy in the form of heat. All right, internal energy is the total energy stored in the particles of a substance. You probably needed that. All right, heat flow. Heat will always flow from the higher temperature object to the lower temperature object. So heat goes from hot to cold. Every single time it goes from hot to cold. Well, why? Okay, well, let's think of this. Remember, temperature is the average kinetic energy of an object. All right, so energy goes from most energy. If we're flowing energy, it goes from most energy to least energy. All right, so let's give you an example. Halloween's coming up, and on Halloween evening or Halloween, you and your friends probably go out trick-or-treating. And if you don't, then somebody does. And when you guys go trick-or-treating, you guys eat a lot of candy, right? Okay, well, when you eat all this candy, you get super duper hyped up. Typically, the energy that you have is going to flow from you out into something else. Okay, it's not going to go, and most of the times, here's a good example, is that your friend is kind of tired and you have a lot of energy, and you go over and you hype your friend up. And so because we would say that would be a flow of energy going from you, the more energetic person, to the less energetic person, your friend. And so it's going from hot to cold. Okay, well, let's think of it going the other way. Why would it not happen if your friend, who is the cold one that has less energy, and you are the hot one that has more energy? How come you don't suck your friend's energy out of them? Well, it's because they don't really have much energy to give, do they? Yeah, so it always goes from hot to cold. It goes from the more energetic one to the less energetic one. Why? Because everything is looking for a balance, homeostasis. We want balance. We want order. All right, so conservation of energy. We know by the law of conservation of energy that energy is not created or destroyed. It simply changes form. Okay, so the higher the temperature, the more energy an object or a substance has. It's more kinetic energy. Okay, and if the hot comes in contact with the cold, the energy moves. Okay, again, what we just said, the hot doesn't get hotter while the cold gets colder. So the hot one doesn't suck out the energy from the cold one that it has, and then it just lays there lifeless and dead. No. Okay, the hot one is going to share. It's going to say, hey, I got some energy. Let me share my energy with you. And so it transfers some of the energy over, and that way they both end up being at a warm temperature instead of one really hot and one really cold. All right, so specific heat. Different materials have different capacities for storing internal energy. So that means that different materials can store different amounts of energy or soak in different amounts of energy. Okay, specific heat is the amount of heat that's needed or required to raise 1 kilogram of a substance by 1 Kelvin. And it has the symbol C. And now notice it's a little c, it's not a big C. Okay, water has a specific heat of 4,186 joules per kilogram times Kelvin. That is the unit that you'll see for specific heat. Joules divided by kilograms times Kelvin. Okay, that's a pretty decent specific heat right there. Okay, so which one has a higher specific heat, water or sand? Now, when we're talking about specific heat, we're talking about the amount of energy that an object can take in before it goes up in temperature. All right, so which one, water or sand, has a higher specific heat? Which one requires more heat to get hotter? Well, think about it. Have you ever been to the beach? Okay, and if you're at the beach on a really hot day and you step down, it's probably about 12 o'clock, 1 o'clock in the afternoon, and you step down on the sand and the sand is burning your feet. Now, it burns your feet. It's so hot. You're doing that little hot potato dance where you're hopping from, foot to foot to foot to foot, and then you find somebody's towel, you stand on it, and then you find somebody's shadow to stand in, okay? Because the sand is hot. But then you go down to the water. Is the water just as hot? Heck no, that water's cold. Okay, so which one has a higher specific heat, meaning it needs more heat to get it hot? Well, if you said the water, you're right. Because the sand only needs a little bit of energy in order to make it hotter. Whereas the water, remember the water, it starts getting warmer when the weather gets warmer. But it doesn't reach its warmest temperatures until the weather starts to get cold again. So water can store a lot of internal energy. It is slow to get hot and it's really slow to get cold. Just like I said, during the summertime, everybody's, oh, the water's so cold. Well, it's so cold because you need so much energy to go into it to get hot. Okay, so by the time, probably November, December gets here, that's when the water at the beach is its warmest, if you were to actually take the temperature of it. Okay, because it's soaking in all that energy from all that hot. And then when the temperature gets cold again or starts to turn cold, it slowly releases that energy back out to cool itself back down. So it's actually at its coldest when the temperature starts to rise again. All right, heat problems. How can we solve these? Well, Q is the amount of heat or energy needed. M is for the mass of the substance. C is the specific heat, and then delta T is the change in temperature. Okay, so energy needed in order to change the heat of something, and then here we need the mass or the number for the mass, the specific heat, and then the change in the number of degrees. Okay, another way to think of this, if you don't like that, is to think of money instead. Okay, so another way to do this is, how much money do I need in order to buy everybody Christmas presents coming up soon? Because Christmas is going to be here in like a month and a half. Like, seriously, people, we don't have time. Okay, 2 months. All right, so the money that we need is the energy needed, right? Money needed. I've got to buy so many people presents. I've got to spend so much money per gift, and I got to get so many gifts. So how much total money do I need in order to buy all of that? It's just another way to think of it. All right. Heat lost is equal to heat gain. Let's talk about that for a second. So, two objects come into contact with each other. One's hot, one's cold. The heat that's lost from the hot one is the amount of heat that's gained from the cold one, so that they end up evening out. Okay, the heat lost by one object is equal to the other. It's called the law of conservation of energy. All right, we need to go through some sample problems. So how much heat is required to raise the temperature of 200 kilograms of water from 25 degrees Celsius to 37 degrees Celsius? All right, so how much heat is required? That we're looking for Q. Okay, let's analyze this. To raise the temperature of a 200 kilograms of water, so we know that this is the mass, we're going to need the specific heat of water, so we'll look at a table for that. And here, this gives us our change in temperature. Okay, so Q is equal to MC delta T. M is 200. C is the specific heat of water. We get that from a table. The change in temperature is 37 minus 25, which would be 12 Celsius. And since Celsius changes on the same scale that Kelvin changes on, 12 degrees Celsius, the change in temperature is the same thing as 12 Kelvin. If you're not sure on how that happened, we'll talk about that in class. All right, so we plug that into the calculator here. We put Q is equal to 200 times 4186 times 12, and we get this really big number. It's huge. All right, well, you can keep that number. You can change it into kilojoules, make it a little bit easier to deal with, right? Move your decimal, or you can change it into megajoules by moving your decimal 3 more times. All right. Okay, example 2. A piece of unknown metal has a mass of, this is our mass, of 2.38 kilograms. It's heated to 100 degrees Celsius, which is our initial temperature, and dropped into 500 or 5.00 kilograms of water at 24 degrees Celsius. This would be our well, that's just telling us the water or the temperature of that. The final temperature of the system, this would be our final temperature of the system. We're looking for a specific heat of this metal. All right, so how do we do that? Well, heat lost by the metal is equal to heat gained by the water. So all we have to do is figure out the Q of the water, and that tells us the Q of the metal. Okay, so the Q of the water, well, our change in temperature would be equal to 67.5 K. Our change in temperature of the water is 8.5 K. So this is the metal, this is the water. Okay, so then all we have to do is take everything for the water and we plug it in. So we put the mass of the water, the specific heat of the water, the change in temperature for the water, and we set it equal to the mass of the metal. We're looking for this, and this would be the change in temperature for the metal. And we solve for C. There we go. All right, endothermic versus exothermic. I got 30 seconds. Endothermic means inside. It means the energy is going inside, is being absorbed. Okay, heat's going in, heat is being absorbed. Exothermic means the exo, outside. Thermo, heat. So heat or energy is going outside, it's being released. Oh, I did that quick. All right, we'll cover this in class again tomorrow, and I'll see you then.